Using an equilibrium constant to predict the direction of a spontaneous reaction. Okay, so basically this is asking us about substituting numbers in terms of concentration, etc., into our equilibrium constant and determine if we're at equilibrium or not. And if we're not in equilibrium, what direction are we going to travel in order to reach equilibrium? So the first thing we have to do is write an equilibrium constant expression. So that'll be the concentration of our products raised to the power of their stoichiometric coefficients, which in this case is all 1 to 1, so that's kind of handy. That's nice maths right there. So the cyanide ion concentration times the ammonium ion concentration divided by hydrocyanic acid concentration times ammonia concentration. Oh, right, so this is our equilibrium constant, and we are told that the equilibrium constant is equal to 1.2. I guess I'll write that in there just to remind myself. Okay, so just a quick and dirty kind of eyeballing. If we have an excess amount of products, so that'd be too much cyanide ion, too much ammonium ion, that is going to result in the number on top in our reaction quotient being too big. So that is going to give us K greater than our equilibrium constant, which in this case is 1.2. So if we see anything where Q is greater than K, so in this case that's greater than 1.2, that is going to tell us that we've got too much product. So my equilibrium will shift to the left. Reaction will go left, which means the concentration of the products are going to decrease and the concentration of the reactants will increase until you get to equilibrium. On the flip side of that, okay, say I have too much hydrocyanic acid and too much ammonia, that's going to make the number on the bottom, on the denominator of my equilibrium constant expression, too big. So K is going to end up being less than 1.2, okay? So my value of my reaction quotient being less than K, so in this case less than 1.2, I've got too much reactants. Reaction will go right, okay, because we need to use up those excess reactants and make more products in order to get to equilibrium. Okay, so I guess we need to actually substitute some numbers in, and then we have to think about it in terms of which ones are reactants, which ones are products, and how their relative concentration will change. So let's just go ahead and work out. So for this one, this is a little naughty. We don't have charges on our ions. Naughty ALEKS. So the concentration of the cyanide ion would be 1.01, and the concentration of ammonium would be 1.2. And then we're going to divide that by, this is nice that we don't have any stoichiometric coefficients, so we don't have to do anything to the power of anything. So hydrocyanic acid 0.36 times ammonia 0.11. So we're going to see what this number shakes out to be and whether it is greater than K, less than K, or equal to K. If it's equal to K, then you've got to be at equilibrium then. All right, give me a second while I calculate. So 1.01 times 1.2 divided by, can I use a calculator? 0.36, debatable, times 0.11. Did that come out correctly? That comes out to Q equals 30 and change. So that means Q is much bigger than K. So if Q is bigger than K, that is telling us that our number on the top is too big. Okay, so that means we've got too high a concentration of products. So the reaction is going to go to the left in order to address that balance. Okay, so products are going to get converted into reactants. So that means my concentration of cyanide and ammonium is going to decrease, and my concentration of hydrocyanic acid and ammonia is going to increase because we are going to the left. Reaction goes left to favour reactants. Okay. All right, so I guess I'm going to have to scroll down. Probably a little bit. Or I can just... no, that's not going to work. Scrolly, scrolly, scrolly. Okay, I'm going to have to get rid of these. I'll leave that for a second if you're still writing stuff down, etc. All right, so new concentration. So new value of our reaction quotient with these concentrations. So our product Cn is 0.19 times 0.38, and then divide that by our reactants 1.18 times 0.93. Okay, I've got a feeling I know which way this is going to go. And don't forget, if your equilibrium constant expression had a power, right, from stoichiometry or whatever, you've got to include that as well. This just happens to be a really simple equilibrium constant expression. Times 0.93 gives me a value of Q of 0.07, which is less than K. Okay, so that smaller value of Q is telling us that the reaction is going to have to go towards the right, because what it's telling us is the number on the bottom of the reaction quotient is too big, and that number is on the denominator is where our reactants are. We've got too much reactions, basically. So my reaction is going to have to proceed to the right to convert some of those reactants into products. So we want to favour product formation. Okay, so what that's going to look like, if I can make my text box obey me. So our reactants are going to decrease in concentration. So our reactants are our HCN and our NH3, and our products should be increasing in concentration. So that'll be our cyanide ion and our ammonium ion. Okay, so I think I'm going to have to scrub some of this stuff so I can scroll down and look at the last question, because I believe there's 3. Let's see what numbers we've got. All right, so for C then, let's do it. So my reaction quotient is going to be concentration of my products on top. So that'll be my cyanide ion and my ammonium ion on the top. And then on the bottom, we'll have my hydrocyanic acid and my ammonia. And I'm going to make that straight, otherwise it will annoy me. All right, so let's calculate Q and then compare it to K, which was 1.2. So I get 0.6 times 0.79 divided by 0.77 times 0.52. I get 1.2. So Q equals 1.2. Q is equal to K. That tells us the reaction is at equilibrium. Yay! So if the reaction is at equilibrium, the rate of the forwards reaction is equal to the rate of the reverse reaction. So there should be no overall change in the concentration of any of our reactants or products. All right, so we've got all 3 possible scenarios when comparing Q to K. Have fun with that.